Okay, so welcome back, everyone. So in this video, we'll continue talking about stationarity test. Just saw in the last video, Dickey-Fuller test. In this video, we'll just look at augmented Dickey-Fuller test. In the augmented Dickey-Fuller test, we are allowing for uh, the delta YT to be, to have some kind of auto-regressive feature. And for example, just a little bit like maybe last period it went up, this period is going to go up just due to momentum. But eventually, it might go back, right? So in that case, we're allowing for it to be correlated with the past change as well as, other lags of higher order, right? So the way we do that is when we specify the equation to test for unit root, we include the lag values of the delta YT as well. Okay. So that, yeah, we're kind of being a little bit more relaxed in terms of, stationary in the sense that the Y series doesn't have to come back to the mean the next period. It might take longer, but eventually it comes back. So the longer the lag values we allow, it means that we're allowing for it to take more time to come back to the mean. Okay, so the equation to estimate is just going to add the uh, lag values of the delta YT, the change in YT. In addition, Dickey-Fuller, the augmented Dickey-Fuller test, it also allows for stationarity around a trend, and which we'll talk about later on, right? For example, the data may have a trend, right? But once we take out the trend, if it's stationary around a trend, we would say, yeah, it's still stationary, but we need to just control for the trend. Okay, so that's the augmented Dickey-Fuller test. Okay? So we add lag change in Y as well as we might add the time trend. I'll talk about the time trend in a second. But in this case, let's just focus on the lag values of the change in Y because that's the main thing. In this case, the test for stationarity is gamma here. Gamma equals 0. Gamma is the coefficient in front of YT minus 1. That's gamma. 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 Looks like that. Looks like a grass blade. Okay. Example, NVIDIA monthly stock price. Now, there's going to be some technical issues with choosing the lag order, right? You can consult other sources. That's not going to be covered in this class. But let's say I pick lag 5. I allow for the stock to come back to the mean, uh, waiting 5 periods. Okay. So I allowed for lag 5. If I allowed for 5 months, is it going to come back? And we look at the p-value again. So the command looks like this: dfuller, the variable name, price, comma, lag, and then the number of lags you want to put. In this case, I want to put 5 lags. The result shows p-value 85% again, right? So in this case, it's still non-stationary. Now, in the previous video, I didn't mention this, but it's worth mentioning here, is that the way it really works, just like statistical test, right? You have your test statistic, and you're going to compare that to your critical value, right? Now, in this case, what we're looking at is we want to have our test statistic to be more negative than the critical value to be significant at that level. So to be significant at 10%, we need our test statistic to be less than negative 0.25, negative 2.598. Right? So at the 10%, this is not significant. This is less negative than 2.598. Right? So you're going to want to compare your test statistic to the critical value. You want it to be larger than the critical value. notice that the the higher significance level, meaning the smaller percent of a mistake, requires a larger test statistic to pass. Okay, anyway, even with augmented Dickey-Fuller, my NVIDIA stock is still non-stationary. So if I start to estimate NVIDIA stock along with other X variables, this is going to be a problem. And so I have to fix that problem. I'll talk about that in a second. Okay, next issue we can discuss is trend stationarity. A time series may be non-stationary, but around a time trend, a linear time trend, it might be stationary, right? So we test for that trend stationarity too, because if it's stationary around a trend, then we can make the series stationary by adding a trend to our analysis. Okay, so how do we estimate trend stationarity? You just do dfuller, variable name, comma, and then type in trend, right? So in the case of NVIDIA stock, I did the same thing. Notice that the test statistic is larger, but at the same time, the critical values are larger as well. So our p-value is still high. So even with adjusting for a trend, NVIDIA stock is still non-stationary, right? So if it's trend stationary, we have to include a time trend in our regression to estimate. But in this case, it's not stationary even with a trend. Next, different stationarity. This is a concept where the series is stationary after the dth difference. Dth difference. D is the order of difference. First difference is yt minus 1, meaning that you take current y minus previous y. That's the first difference. Okay. Second order difference is the change in y this period minus the change in y last period. That's second order difference. Okay. So the difference in the change. Third order would be the difference in the difference in the change. And so it gets a little bit more harder to wrap your head around, but it's not about taking the difference with the further lag values. No, but it's about measuring the change in higher order. Today's y minus last period's y, that's first difference, right? The change from period to period. Difference in the change, that's second order, second difference. Difference in the change, that's a third order. Okay, so typically we only deal with the first difference. And we'd say it for short, different stationarity to mean that the series is stationary after first difference. Okay. So different stationarity, we're talking about first difference. If the first difference is stationary, then that variable is different stationary, also known as I1. Okay, anyway, let's check NVIDIA stock. So the command is dfuller. Now, instead of testing the stationarity of the price variable, we're testing the change in the price, d.price. Okay, and what we see here is the test statistic is quite large, 7, right? It's larger than the critical value at 1%. And so this is definitely significantly stationary, right? It's stationary. The p-value is almost 0. So the first difference is stationary. Okay. Now, this means that for NVIDIA stocks, if we want to estimate the model with explanatory variables, we need to take first difference to make a meaningful estimation. Okay, so I'm going to just end the video here and pick up on the next topic.